Hi, and welcome back, kiddos. We just have a couple more problems to work here. Again, we want to start with our balanced equation. So we have chlorine this time reacting with lithium bromide. Now that's an ionic compound. Ionic compounds are typically going to be solids. And it's a single replacement. You should be able to predict these. And then we would get bromine liquid. Now you notice that our only gas is the chlorine gas. So that's the only thing to which we can apply our ideal gas law, Pevnert. Now we're given our starting conditions of 4.5 liters and 600 torr and 298 Kelvin. Fortunately, we're given excess lithium bromide, which means we don't need to do a limiting reagent problem. And it asks us how many milliliters of bromine. Now, it's important to note that we're also given the density of 3.12 grams is the measurement equivalent of 1 milliliter. So if we can get to mass, we can get to milliliters using this as a conversion factor. But we're going to first start by doing a formula before we can hop into our dimensional analysis using Pevnert. So we have 600 torr, 4.5 liters, and that's going to give us our moles of chlorine. Remember, you can't use this for moles of bromine. You have to use that mole ratio first. Even if the mole ratio is 1:1, if you skip that mole ratio, you will lose points. So 298 Kelvin. So my moles of chlorine, if you do that algebra, are 0.145 moles. Now we can use those moles and we can pop those into the more conventional dimensional analysis that we did with our last unit. If I can get a straight line showing up here. There we go. So, got a dimensional analysis. We've got moles of chlorine. We're going to have to take moles of chlorine to moles of bromine, then moles of bromine to grams of bromine, and then to milliliters. So let's start. We've got 0.145 moles of chlorine. We want chlorine to cancel, so we're going to put moles of chlorine in the denominator and moles of bromine in the numerator, and that's a 1:1 mole ratio. And don't forget, it's Br2 because it's diatomic, so its molar mass is also doubled, grams for every 1 mole of bromine. And now we only have one more step. All we need to do is use the density to get to milliliters. So the density tells me that for every 1 milliliter I will have a mass of 3.12 grams. And if you do that algebra, you should get 7.43 milliliters. Okay, one more just to re-emphasize this movement back and forth. This time I have solid sodium carbonate. Again, if it's a solid, you cannot apply the ideal gas law to it. I don't want to see that on your test at all, plugging in values for solids into the ideal gas law. Sodium oxide is also a solid, but it's our CO2 that's the gas where we'll get to apply our Pevnert. So let's write our givens underneath. Now this is 450 milliliters. Be careful of units here. 800 torr. And let's jump right into the world of Kelvin. 318 Kelvin. Now if I have this information, I can get moles using Pevnert because it's a gas. So I can use PV is equal to nRT. And then I can go moles to moles. And then I can use moles to mass using molar mass. Now, be careful. Because of R, the units of R, we're going to use 62.4. It's liters torr per mole Kelvin. So that means that my volume has to be in liters. So I have 800 torr, and that's 0.450 liters is equal to our moles times 62.4 times 318. Squeeze that in there. So my moles of CO2 is 0.0181 moles. So now I can go, now that I've used my ideal gas law, again, you can either use it to get onto the mole road or off of the mole road. This time we used it to get off of the mole road. So we've got moles of CO2, we've got to go moles to moles, and then moles to mass. And then we're done. So pretty short movie again, and hopefully you're picking these up. This is moles of CO2, and it's a 1-to-1 mole ratio yet again. I think it'd be worth making new videos just to get rid of all these 1-to-1 mole ratios. So, and that's 1 mole of CO2. I wanted moles of CO2 to cancel. Now I want to eliminate moles of sodium carbonate, and I want grams of sodium carbonate. Moles to mass use, molar mass, 105.99. If you crank through that math, should get 1.92 grams. All right, it's plenty of stoichiometry to lay that out. We'll have some time to practice and work on our homework packet in class. So until then, this is signing off.